This is a talk for the virtual MathPsych and ICCM meeting 2024 on the topic of time-variant payoffs and signal detection theory. The principle better safe than sorry, the claim that a false positive response is less costly than a false negative, is often used to justify what would otherwise seem overreactions to rare events. It is used to explain pareidolia, the tendency to see faces where there are none, which is assumed to be less costly than not noticing a face when there is one. Or the tendency of men to believe women are sexually attracted to them. This informal idea can be formalized using signal detection theory. Under the name error management theory, this application of signal detection theory has made it into evolutionary psychology and has been generalized to other problems. And it also shows up in psychiatry and medicine under the name smoke detector principle. For an illustration, assume you had a list with the surnames of the women and men shown here with their heights, and you were asked to say yes or no to the question, is this a man, using only the heights. Where would you set the decision criterion? If I set the criterion at the yellow line and call everyone taller than that a man and everyone shorter a woman, is that the best place for the criterion? If you shift your criterion from the yellow to the blue line, the two men at the front, whom you previously correctly identified, now become false negatives. But the 19 women in that row turn from false positives to true negatives. If you were paid the same for each correct answer, the blue line would be a better decision criterion. A further shift from blue to green would reduce the proportion of correct answers. 6 women go from false positives to true negatives, but 7 men go from true positives to false negatives. That argument generalizes to distributions. Shifting the decision criterion, the red line, from its current position to the right increases correct decisions because the area under the green curve, representing former false positives that have become true negatives, is larger than the area under the blue curve, representing former false positives that have become true negatives. Generalize the argument to any location and infinitesimally small shifts, and the optimal criterion is where the two curves cross. If you let the curves represent frequency as well, for example, let the curves represent a psychology class ordered by height with 4 times as many women as men, then the optimal decision criterion is still where the curves cross, but it is no longer halfway between the means of the two distributions. The same would happen if we still had equal proportions of men and women, but women were 4 times as important because you get 4 times as much for a true negative than a true positive. If the height measurements were really sloppy, increasing noise, the optimal decision criterion becomes more extreme. So the optimal decision criterion is determined by frequencies, payoffs, and distance between the means measured in standard deviations. Of course, there is an equation which expresses that relationship. However, in the example I gave, the point was not to find the optimal decision criterion, but that evolution was assumed to have optimized the decision criterion and to infer the relative magnitude of payoffs. So the equation needs to be solved for that. One of the key assumptions that signal detection theory makes is that payoffs are constant, independent of time, discriminability d prime, level of effort, or anything else. However, in many of the cases when signal detection theory is used to explain an apparent overreaction to rare events by appeal to asymmetric payoffs, payoffs are not constant. A fundamental assumption is violated. So the question is whether even a qualitative conclusion, such as false positives must have been less costly than false negatives, is still valid when trying to explain a bias to answer yes to questions such as, is this a face, or is this a predator, or is she into me? So if payoff is a function of time or a function of discriminability d prime, are there sets of functions that make it impossible to derive from the decision criterion whether the payoff ratio is larger or smaller than 1, or equivalently, whether the logarithm of the payoff ratio is larger or smaller than 0? If such sets of functions exist, and there's a plausible case that they are relevant, then signal detection theory can't provide valid inferences regarding payoffs. In the title and abstract, I refer to payoffs varying with time. Griffith et al. Showed that if information is being gathered over time, that can be treated as an increase in d prime over time. That alone would still give unique solutions and therefore valid inferences, because it would only shift this scaling factor. But a case can be made that responses and therefore payoffs depend on d prime. Then it becomes easier to treat payoffs directly as a function of d prime, which is what I will discuss, and how I should have phrased title and abstract. So let's imagine that your problem is to work out not whether someone is in the binary state of either angry or not angry, but where they are on a continuum from zen to homicidal. So we abandon the assumption that the possible states of the world form discrete categories. Next, assume that your response can vary continuously in intensity and that payoffs vary continuously as well. Start with a payoff for a false negative. You fail to notice anything. The more angry the other person is, the more they harm you until they reach the limits of their powers. That is a sigmoid curve, and I chose a cumulative Gaussian for its tractability. That is a red curve here. The blue curve is for the false positive. You act to mitigate the other person's anger when it is not necessary, and that action costs you something. But you are reasonable and only start to act when there's reasonable evidence. The inflection point of this curve is at d prime equals 2. For the true positive function, I chose a difference between two Gaussians. Because you need reasonable evidence before you act, initially you suffer the same cost as if you had failed to notice. Then the more obvious the other person's anger is, the better is your excuse for doing what you have been wanting to do anyway, and things work out just fine for you. And if there is a true negative, nothing happens, and so I left that payoff constant at 0. I rather thought there was enough going on there for strange things to happen, but it turns out the conclusions you can draw are remarkably robust against some variations. It turns out that the log payoff ratio for this set of functions is independent of d prime, as if I had kept all payoffs constant. When I plot the optimal decision criterion as a function of d prime, of course, it looks exactly as in Lin and Barrett's 2014 paper, where payoffs were constant. And finally, I want to know what inferences can be drawn about the payoff ratio from the decision criterion and a low base rate. So I plot those against each other. And for the whole range of decision criteria, here I find the same log payoff ratio. Absolutely everything looks like it does when payoffs are constant. Then I decided to try a slightly different payoff function for the true negatives. I don't have a rationale for this linear function, I just wanted to see what happens. Weird and wonderful things, it turns out. That little change makes a big difference to the log payoff ratio as a function of d prime. That in turn changes the optimal decision criterion as a function of d prime. And When I plot those against each other, I find that there are values of d prime compatible with 2 or even 3 different values of the log payoff ratio. That is not yet a catastrophe. The inferences in the literature are qualitative. Nobody has quantitative estimates of base rates over evolutionary time spans, so quantitative predictions of log payoff ratios are impossible anyway. All anyone ever argues is that this outcome is more important than that outcome, meaning they argue that log payoff ratio is larger or smaller than 0. And the inferred payoff ratios in this example are still all negative. But a quite small change in slope of the true negative cost had quite an effect. So let that slope steepen a little more. All the effects are stronger, and that includes a range of decision criteria compatible with both positive and negative log payoff ratios. And it gets worse if you let slope increase a little more. So signal detection theory assumes that 1, successive choices are independent. Trimmer et al. 2017 and McNamara and Trimmer showed that violating this assumption can change predicted behavior drastically. They did that already, so I didn't deal with that. 2 possible states of the world form discrete categories. 3 responses are not graded but binary. And it follows from that 4 that payoffs are constant. I violated the last 3 assumptions and found that can invalidate the qualitative inferences that have been drawn from signal detection theory in the biological and behavioral sciences.